Yeah, it's the night before Advent of Code 2020 kicks off, so I'm excited. I think it should be fun, but we're gonna probably just take it easy tonight. Maybe stream for like an hour or so. Look at a few problems, but otherwise conserve our energy. Not that problem one is usually that much of a problem, but just on principle. So let's get right into it. I think uh, I'm still looking for opportunities to add to my utilities that I'm trying to build up. Um, the only new one that I have is this spaces function, which it doesn't care if they're digits or spaces or whatever. It'll just separate the input on spaces. So pretty much every other language has a built-in function for this. So uh, I feel like we should have a pre-constructed one as well. Um, yeah, and I think that's about all I have to say. So let's go ahead and just jump into some problems. Oh, I noticed looking at the recording of my stream, what was it, Friday night? My camera died, and I was stuck in like this weird pose for the last 20 or 30 minutes of the stream. So if you see that happening, it's not your internet. Just go ahead and message me on chat, and we'll see if we can do something about it. Speaking of, uh, I should probably sign into chat on my phone so that I can see what people are saying. Uh, Give me 1 second. Okay, there we go. Cool. So where do we leave off? So problem 12, I kind of rushed this, um, but yeah, this is basically a strongly connected components problem. Not much there. We are on problem 13. Packet scanners. You need to cross a vast firewall. Your puzzle input, what does our puzzle input look like? 2017-13. Okay. Digits. I think we want to mix that. Oh, I'm not calling it digits, I'm calling it ints. Okay, great. There's a layer immediately inside the firewall with range 3, a second layer immediately after that with range 2. Back and forth within its range. Starts at the top and moves down until it reaches the bottom. You are caught. The scanner moves into the top of its layer while you're there. You are not caught. Okay. Sure. You are caught in layers 0 and 6. Uh, you're not caught in layer 1. Equal to its depth multiplied by its range. Okay. So they go back and forth, right? They don't just teleport to the beginning. Yeah, alright. I think this is basically like a modular arithmetic problem. Um, so if we had a range of like 3 boxes, I can close this. Okay, fine. If we had a range of like 3 boxes, it starts at 0, goes 0, 1, 2, 1, 0. So it takes uh, 1, 2, 3, 4 steps to get back to the beginning. Um, hmm. So if we took like 3 times 2 mod uh, it's kind of, it would be 2, but it skips at the end, so it would be -2 plus, yeah, 4, right? And if we had 5, it would take 8 steps. If we have 4, so at picosecond 6, this thing goes back to 4. Um, sorry. Yeah, okay. So basically what we're doing is we want the right tack P, this is all of our widths, and we want 2 times neg2 plus, and then this is how long it takes. So they all start at 0, but they don't really start at 0. They start at these ranges. So that's left tack P, and this is going to be plus mod right tack. Uh-huh. And the question is equal to its depth multiplied by its range. So this will be 0 equals gives us a Boolean matrix, and then we can reduce first on P, right? Depth multiplied by its range, and then the sum. So like this, 1904. Yeah. All right. We need to pass through the firewall without being caught. Easier said than done. Can't control the speed of the packet, but you can delay it. Oh, and the question is fewest number of picoseconds. All right, so we can probably just brute force this. So we'll start this at 0, and then we'll say if 0 inner product equals this, then W. Except this is W plus here, I'm pretty sure. Otherwise, we recurse on W plus 1. See if we get an infinite loop. I really have no idea how long this will take, but it feels brute forceable to me. There's probably some mathematical trick here, some modular arithmetic. I should look into that because I've seen these sorts of problems in previous years. Um, is this Can't tell if I should stop it or not. All right, sure, I will. Let me just, rather than recursing here, just tell me what this is. So if I do it with 0, oh, that's interesting. Oh, yep. So if I do it with 0, I get the same as before. If I do it with 1, yep, that increases things. I think actually, I think this is correct. I think it's just a really, it takes a while to brute force, unfortunately. I do kind of, I have the answer. I've solved it before at some point in time, so I could kind of cheat and look at how big the number is. That's not viable in the competition, obviously. Is there anything I can do to speed this up? Looks fairly performance. All right, let's look. I've heard some of this talk about the Chinese remainder theorem. Uh, should look into this. Then one could determine uniquely the remainder of the division n. Some of these Wikipedia explanations are uh, not actually the best way to learn these concepts. It's been a while since I took a math class. Ring isomorphism, huh? All right. That's still cranking. N1 and N2 are coprime. I don't think any of these are coprime. Do I have anything in defense for this? Let me switch keyboard. Apparently not. Hmm. I mean, this is more efficient than uh, doing the actual simulation. Oh, hmm. Maybe something with like least common multiple, greatest common divisor. Hmm. So we're adding a delay. fewest number of picoseconds you would need to delay to get through safely is 10. Um, well, let's just see. Hang on, let's try this test data. So what is this? This is 0, 3, 1, 2, 4, 4, 6, 4. This is 4, 2 row. Is that right? Or 4? Yep. Let's call this T. And then let's just see if this gives us 10. No, it doesn't. So we have like an infinite loop situation here. Um, hmm. Get rid of all this. Get rid of this. 2, 1, 2, 4. So apparently adding there isn't what I actually want. Is it adding over here? No, that would be weird. State after delaying. The function works though, it gave us part 1. Right, so nothing's changed there. 1904 here. The delay should be added to the depth. Right? Here 140. Oh no, wait a second. X4. Iota 10 for each. No, I'm in index origin 1, but I'm not doing any indexing here, so it shouldn't really matter. Two one two four. Hmm. Looks fairly performance. Yeah, that can be my catchphrase, Ellie. uh, so what is going on here? So if I do this, let's say I do like iota 20, I don't know. I don't think, yeah, it's not like an off by one error or anything. Um, oh, geez. Wow. I am absolutely reading the problem wrong. It is not 0 equals across, it's that 0 is not in the result. Because you don't want to get caught, right? So you can see here in the first, yeah. All right, I'm an idiot. So you can see here in the first 9 results there's zeros, and then the first one where there aren't any zeros is index 10. So if instead we say 0 uh, in not, then W, else recurse on W plus 1, and we start this at 0, then it'll give us 10. Okay. This might still take a while to run, but at least we're looking at the right problem. All right, well, so lesson learned for the actual competition, as happened, last year as well, is that you should actually read the problem and not make assumptions about the problem you're trying to solve. We will try and remember that. Yeah, 3833504, which is the answer. So, yeah, it is like a pretty simple modular arithmetic problem. I was just looking for um, the wrong solution criteria. All right, number 14 activates the system's disk defragmenter. I remember doing this actually. This was great in the 90s. You could just sit and watch defrag. Um, not hashes. Oh, right. I may actually skip this one because I don't think that I saved my code that I was using for not hashes. And if I remember right, it was a pretty beefy function, so I don't really want to derive it again on stream. Um, yeah, let's put this one on hold, and we will come back to it um, once I actually write down the code for the not hash problem. Dueling generators, generator A and generator B. Compares the lowest 16 bits of both values. Wait, what does my problem input for this look like? Uh, it's 15, right? Sure. just enlist. All right, great. So that's P. Multiply it by a factor. Generator A uses 16807. Okay. Our factors, 16807, and what's the other one? 48271. And we have some remainder thing. This is 2 to the 31st minus 1. Is that right? Apparently not. Oh, right, order of operations. Yeah, okay, so it is. Might be useful. Calculate each generator's first value. Instead uses specific starting values as previous value. $40 million pairs. Great. Okay, so we have a counter, and we are going to start with our problem input as the initial value, and this is going to be fax times omega. Start this as like new value. Actually, it should be, yeah, like so. Final remainder is the value it produces next. Okay, and then with this, we need 16 row 2 binary decode. Encode, I always get these mixed up, and I think that just takes the, oh dear. This should just take the rightmost, reasonably sure actually. Let me just check. 16 row 2 encodes 4190. Better, oh, I don't know. 2 to the 16th. How about that? Yes. Okay, great. Cool. And then here we're just going to do equal reduce and reduce. And if that is true, then C gets 1. Nope, I cannot do that. So what I'll do instead is I'll take the value of this, add it to C, right? And then we can recurse on the new value. And apparently we were going to run this 40 million times. What is that? 4040 000 000. And then finally just give me the counter. Yep. This is again one of those solutions where I'm like reasonably sure there's some mathematical way to do this. We're dealing with remainders again. There's 40 million, right? There's 400 million. All right. Cool. Fair enough. Oh, hey, we have some people in the chat. Um, we have Userman2. APL is such an interesting language to spectate for me. Well, I'm glad. Yeah, come hang out. We're happy to have you. If you have any questions about APL or anything, just feel free to uh, drop uh, ask in chat. Then we have a spammer, which I guess means that I've made it to the big leagues. All right, how long is this actually gonna? I didn't think that it would take this long to run this. What am I doing? Sorry. Wow. I don't know why I'm recursing and using the power operator. These pairs are yada yada yada. I could also just take the remainder of 2 to the 16th. Uh, what is that? 8192? I think I can avoid doing this sort of binary conversion. I guess this is fine. If this takes too much longer, I'll have to go back and run the test cases to make sure that the logic is actually sound. 65 and 8921. That doesn't seem right. Right. What is 2 to the 16th? 65, 536. Um, maybe I can just do that. 2 to the 16th. Remainder. Uh, is this... I can't do this. This isn't a vector operation. P, 618. Yeah, like so. Oh, because I'm asking for C. Equals, then C plus 1 in V, else in V. And give me C. Ugh. Yeah, that makes sense, because, like, say we were looking at the last 2 bits, then, like, 7 and 3 would be equivalent mod 4, which is 2 squared. So, I think this is a more efficient way to do it. 577. Yeah, okay, great. Um, in the interest of trying to align a little bit better, they only hand a value to the judge when it meets their criteria. Each generator functions completely independently. Uh-huh. After 5 million pairs. Okay, sure. So A and B will be 2-row enclosed Zilda. We're just going to throw some numbers in there. If Oh, but this will be tricky with conditionals. What if I just have one like this, and this will be 0, 2 row, and then we'll just say, how does this work? If I do like 4, 8 mod 5, 7, this applies for each one, right? Okay, cool. So we'll say 4, 8 mod this will be like new out 4, 8 mod or equals. If any one of those are correct, then out no in V, otherwise in V. This time only 5 million C6, right? Boolean singleton value required. Oh, sure. So this is only appending to the output array if one of them is divisible by 4, one of them is divisible by 8. So now now we can transpose this and split it, and we'll call these A and B. And then we only want to select A where it's divisible by 4. So A for mod 0 equals A split. How many is that? Similarly, we want to do this with B. It's much fewer. Call this, call this B, call this A. Um, it'll extend out to the longer one. Well, if I just do like A 0.5 B, then I equals reduce first, and count, what do I get? Link there. Oh yeah, because they're different links. Um, which one was the longer one? Yeah. Length B, take A. 36? That seems low. Indeed it is. No, I think, Or are they not doing the binary thing anymore? They're not. Oh, this 4-8 thing happens before we do the binary conversion. Hmm. Yeah, I mean, that's actually easier. So now I can just do this. I don't care about C, but out should be 0 to row Zilda. And now I can do 2 times 16 mod out equals, no, because I have to do the filtering first. It is 4 and 8, right? 2 to the 16th mod, I can do this here. Wow, still 36. Okay. Well, let's get the values. This is, oh, it's like a 10 megabyte array. And then for out, see if I can just do this all in one line to make it easier. A is for mod A, 0 equals B is right? Then the min length is what is this? Length for each AB min, and this is ML take A, ML take B, sure. Mod. So I don't think that's accurate. Hmm. Did I get these backwards? No. Something else that I missed? Oh, it's 5 million. I see. It's until there's 5 million total. I don't know why I'm getting such a huge number here, but, huh, okay. Oh, well, because I'm not filtering, not that it matters. Yeah, okay. I don't really have a better way to do this than sort of gross conditionals, so, um, so we'll keep doing this until, uh, this will be A, B, 2 row enclosed tilde. Um, if for mod the first one of n value, well, okay, so for 8 mod n value equals, and both of that's true. Even do like that. Then A gets first NV, B gets last NV, and we want to return NV. Otherwise, 0 equals 4 mod first NV. Then we just say that A gets first NV, NV like so. Otherwise, 0 equals 8 mod last element in NV. Then B gets first element of NV. NV, and now we are running this until less than or equal to length for each AB. Oh, sure. Otherwise, just MB. Yeah. And this is going to take a lot longer because we're not just running it 5 million times. We're running it until we get 5 million pairs total. Okay. And then it's just A times B 2 times 16 mod sum equal reduce. Oh. Sure, man. Length B take 316. There it is. All right. Well, it was a long road to get there, but we got there. There's got to be a better way to do this, right? I don't know one offhand. Anyway, all right. So we only got through, what was that? 2 problems? What was the first one we did? This one. Oh, yeah. This one should have been much easier, but I misread the problem. So, as always, the answer is to read the problem carefully. Because I think on the second one also, I kind of, um, I didn't know that the judges here wanted 5 million candidate pairs. I thought we were just looking at 5 million total, so. Yeah. Anywho, I think we'll call it there, honestly. So I want to try and conserve my energy for the contest tomorrow. And oh, look, it looks like my camera didn't stop this time, so that's good. Great. Well, if you tuned in, Userman2, I don't know if you're here still, but if you are, then thanks a lot for dropping in. And yeah, I will see you tomorrow for the start of Advent of Code 2020. All right. Thanks.